So I have two different definitions for the function d over here. Over here, d of t is equal to 3t plus 1. And we could imagine that d could represent distance as a function of time. Distance measured in meters and time measured in seconds. And so over here, when time is 0, right when we're starting, our distance is going to be 1 meter. When after 1 second has gone by, our distance is now going to be, so 3 times 1 plus 1 is going to be 4. Our distance now is going to be 4 meters. After 2 seconds, our distance is going to be 3 times 2 is 6 plus 1, it's going to be 7. It's going to be 7 meters. So given this definition of d of t, this function definition, what is the rate of change of distance with respect to time? And let me write it this way. What is the change in distance, the rate of change of distance with respect to time, which people sometimes call speed? And this triangle right over here, that's the Greek letter delta, just means change in distance over change in time. Well, what is this going to be? Well, let's just take 2 points. Let's just say the change in distance over change in time when time goes from time equals 0 to time equals 1. So over here, our change in time is equal to 1. Our change in time is 1. And what's our change in distance? Well, our change in distance, when our time increased by 1, our distance increases by 3. It goes from 1 meters to 4 meters. So our change in distance is equal to 3. So it's going to be equal to 3 over 1, or just 3. And if we wanted the units, it would be 3 meters every 1 second. And let's think about it. Does that change if we pick any other 2 points? What if we were to say between 1 second and 2 seconds? So between 1 second and 2 seconds, our change in time is 1 second. And then our change in distance is, our distance increases by 3 meters. So once again, our change in distance over change in time is 3 meters per second. And this is all review, and you might recognize, well, we pick any 2 points on this line here, and we're going to have the same rate of change of distance with respect to time. In fact, that's what defines a line, or one of the ways to think about a line or a linear function, is that the rate of change of one variable with respect to the other one is constant. And in this particular one, when we're talking about the rate of change of the vertical variable with respect to the horizontal one, we're talking about the slope of the line. This is the slope. This line has a slope of 3. That's what defines a line, or one of the things that defines a line, is the slope between any 2 points is going to be exactly 3. And just as a little bit of review from other algebra you've seen before, you can even pick it out in the function definition. It's actually written in slope-intercept form right over here, where the slope is this 3. And our d-intercept, when t is equal to 0, is going to be equal to 1. And all of this is review. And if any of this sounds foreign to you, I encourage you to watch the Khan Academy videos on slope and slope-intercept form and things like that. But this is all background to get us to this curve over here. Because this is interesting. Because here, we're no longer dealing with a line. We actually have a curve. And this curve right over here is a quadratic. It's a parabola. And let's just say distance as a function of time was defined this way. Instead of it being 3t plus 1, it is t squared plus 1. And what's interesting here is that the rate of change, you can visualize it, is it's always changing. For example, if you were to pick an arbitrary point on this curve, and if you were to think about a tangent line to it, a tangent line, a line that has the same slope for just that one moment and just touches on it, over here it seems pretty positive, while over here it still is positive, but it seems a lot less positive. So it looks like the rate of change, is actually changing here. It actually, in this case, it looks like the line is getting steeper and steeper and steeper as time goes by. Or another way to think about it is our rate of change of distance with respect to time is increasing. It's not just constant. It's not a constant slope. The slope is increasing as time increases. So for something like this, how do we think about rate of change? How do we think about rate of change of one variable with respect to another, in particular, distance with respect to time? Well, later on in your math careers, you'll find out that this is actually what most of differential calculus is all about, and you will get to differential calculus. But for our purposes, we have another tool at our disposal, and this is actually a good foundation for the calculus that you will learn in the future. And this is the notion of average rate of change. Let me write this down. average rate of change. I already hopefully gave you an argument why it's very hard. You'll need actually calculus to figure out the instantaneous rate of change, the rate of change right at that point, the slope of the tangent line. That you're going to need a calculus. But to figure out the average rate of change between 2 points, we can use very similar tools that we use to figure out the slope of a line. So for example, we could figure out the average rate of change between any 2 points, any two points on this curve. So for example, we could say the average rate of change from when we go from t equals 0 to t equals 3, that's going to be the slope of this secant line. So let me draw that. So let me do this in a more fun color. I'll do it in this color. All right.
It looks like f of x is getting closer and
So
closer to
as I said,
4,
the actual
which is
instantaneous
f of
rate of change
-2.
is constantly changing. In this case, it's increasing, and we'll need calculus for that. But now we could think about average rate of change, which would be the slope of the line that connects these 2 points. And once again, it's only an average rate of change. And as we see the actual curve, its rate of change is slower earlier on, and then its rate of change is higher as we get closer and closer to 3 seconds. But the average rate of change is going to be the slope of this line right over here. And we could think about that. This is going to be our change. So the slope of this line is going to be our change in distance over change in time. And an average rate of change, especially when you're talking about a curve like this, it depends on what starting and ending point. This is the average rate of change for the first 3 seconds is going to be. Well, what is our distance at the end of or right at the 3rd second? Well, it's going to be d of 3. And what was our initial distance? It's going to be d of 0. So this expression right over here is going to give me my change in distance. It's going to give me my change in distance right over here. Let me write it. Actually, maybe I could do it this way. So I could do it over here. So our change in distance is this change in distance, which is d of 3 minus d of 0. So it gives us this height. And then we want to divide it by our change in time. Well, we finished at 3 seconds, and we started at 0 seconds. And notice, all this is change in your vertical axis over change in your horizontal axis. So it is just the slope of this line right over here. So what is this going to be? Well, d of 3, after 3 seconds, 3 squared plus 1, we're at a distance of 10 meters. And at time 0, 0 squared is just 0 plus 1, we had a distance of 1 meter. So our change in distance is 10 minus 1. It's 9 meters, and you see that right over here. Our change in distance is 9 meters. We go from 1 meter to 10 meters, and we increase 9 meters, so that's why it's a positive value. And our change in time, we see time increased by 3 seconds. So divided by change in time is 3 seconds, and so this is going to be equal to 3. And if we care about our units, which it is often useful to care about, we see that the numerator here, that's in meters, so we'll have a meters in the numerator. And down here, our change in time, that's going to be in seconds. So our average rate of change over the first 3 seconds is 3 meters per second. Once again, it's not the exact instantaneous rate of change at any moment. That is actually changing, but it tells us our average rate of change. And we could also think about our average rate of change over other durations. We could think about what is our average rate of change between the 2nd and the 3rd second. So this one is going to be the slope of this secant line. And so over there, it's going to be our distance at 3 seconds minus our distance at 2 seconds over our change in time. We finish at 3 seconds. We started at 2 seconds.
d of 3 is equal to 10. d of 2 is equal to 2 squared plus 1 is 5. So we're going to have 10 minus 5 is 5 meters over 1 second. So we could write it as 5 over 1, or we could just write it as 5 meters per second. And this is interesting. Our average rate of change from time 2 seconds to time equals 3 seconds is higher than our average rate of change from 0 to 3 seconds. And so it's an interesting thing to think about is what happens as our change in time gets smaller and smaller and smaller. And that's actually what we're going to be thinking about in calculus.